let's continue. We change topics to IoT, and Davide will talk about heat pumps in IO state and this estimation of in real time. It's all yours.
Good morning, everyone. My name is Davide Poggiali. I'm from the north and eastern Italy, and I work at Far Networks, which is a Milan-based company in Italy. I'm talking about a real-time estimation of an heat pump state, on or off, with the IoT data. So that is the summary of my intervention. I will give you a quick introduction, and we will talk about the story that gives birth to the data, and that will be important for us. We'll give some pre-processed steps, and so a comparison between some machine learning models, a choose of the best model in some sense, and the conclusions. So this is a case study of the estimation of the state of a heat pump, given some very simple accelerometer data. This is the one that your mobile phone probably has, the accelerometer data. I really hope that this can be useful for your work, for your future work, or inspiring in some way. Now, the rising of the energy prices has given to this work a higher priority in my schedule in the past months because the real-time input on and off, so the real-time on and off state, which is the output of this work, is directly proportional to this consumption in electricity term, so of each heat pump, so you can have an estimate somehow of more or less consumption with that data. So let's talk about the story that generates the data. Now, every data set has a story to tell, and in my opinion, it is pretty important to sit down and listen to the data and spend some quality time with your data. And so let's give some context in here. So the data I'm using comes from Arduino accelerometers, and it's both in all the heat pumps in private clinic in Milan, in Italy. So the heat pump serves for air conditioning, but also for cooling medical equipment. This is how the data is gathered in our context and by my company specifically. There are many sensors of many measures that gives data to an edge computer that can be an Arduino or a Raspberry Pi 2 or whatever computer you can think of, that send via MQTT data to the LARA system, which is our product. The Arduino itself gives also the measure that we're interested in. So all the sensor installed in an environment is sent to LARA via the edge computer and stored in a time value format for future retrieval. So all the sensors were installed and linked to LARA, and all I had to do is go and fish the data. So accelerometer data comes in 3 axes, Y, X, and Z. So we have 3 time value sequences where the time of X, Y, and Z is the same. Let's take a first look of the data accelerometer. Now, these are the 3 axes, and you can see that it kind of looks like a sound. For those who are interested in sound recording, it's something quite similar because it's vibration, and you can recognize where for sure a heat pump is off from here. There are so other sensors, and we'll talk about this later actually, but there are other accelerometers in other stuff in the same clinic. Now, let's take a first look at the data, just the x-axis to begin with. What do we see? There are some hours, and we know it's in the nighttime, where for sure the heat pumps do not work. So this is an off state all around for sure. We have some higher values which possibly, we're not sure if the heat pump is working, but if we zoom in, maybe in here that is a bit lower, there is a tiny little area where the thermal equilibrium is reached, so the heat pump is not actually working while here. So we also see that there is an offset for this data, which is about -1, -0, 15, and we may want to standardize it. This offset may change slightly because the Arduino might move a bit, or somebody can enter a room and move it a bit. So what we want to do is calculate just the moving average, which is that one, and just normalize the data by setting data equal data minus the moving average, so the offset will be 0. So this is our very first normalization step to take. Now we know that the average is about 0. Then, what can we do? As I told you before, there is sometimes in which we're totally sure that the value is 0. So the very first naive idea that can come to your mind, if you know something about basic statistics, is calculating the z-score. So you take the mean, which is about 0, the standard deviation of when you're sure that the heat pump is off, and calculate for each one of the time data the z-score, and set a threshold. If the z-score in absolute value is more than, say, 2 or 3 or whatever you want for threshold, you consider this as possibly, very much probably, not a 0 state, so you can set it to 1. This is pretty much naive, but it comes with an hypothesis that, well, this data follows a normal distribution, and not all the distribution are normal, so we have to move a bit on. We have no labels yet. We just have some sure zeros. So let's move a bit on. How to get more labels? Just recall the story of the data. The heat pumps serves for cooling or heating the rooms, but also for cooling medical equipment. So we have a magnetic resonance with another sensor, and as we know, the magnetic sensor, the magnetic resonance vibrates a lot when it's used. And when the RMI is on, for sure the heat pump is on. Otherwise the resonance will break and we will throw away a lot of money. So we can use the accelerometer in MRI scanner for giving some time in which the heat pump was on for sure. Let's take a quick look on the accelerometer data. Oh no. Okay. There are many outliers, so I can have an outlier detection and drop some data out that will be useless, totally useless. Let's do it. There are also some times in which the sensor gave no data, which are those straight lines in here. Alas, there are a lot, but I see a lot of times in which I'm pretty sure that the heat pump was on. So I can just see everything in here and patiently label some data by hand. Now with some patients, I have individuated some intervals in time in which I'm sure the heat pump was on or off, seeing all the data. And so 10% of the data now has labels. So we can move on. We can just drop all the unlabeled data and try to do something with the labeled one. Now we choose some popular binary classification models as provided by scikit-learn. the logistic regression, the support of vector machines, random forest, naive Bayes, which is some similar thing that we did before with the z-score, if you think about it, and the key nearest neighbor. And we will compare the performances after a train test random splits in terms of accuracy, precision, recall, receiving operating characteristic area under the curve, as the closer to 1 the better, the closer to 0.5 the worse, and evaluation times in my laptop, just to have a comparison stone. Now these are the results. For some reasons, the precision and accuracy of the first two were low, and the rock AUC, it's low too, but the last four are very much better with a rock AUC close to 1. So, how to choose? My goal is to have a real-time estimator. So, there is no problem in here because the data comes at each second at its best. So I cannot set more than one data point for a second. So every one of them is in principle good, but the fastest of them is the naive Bayes, which has a pretty good rock AUC and accuracy, precision, recall compared to the others. So that's the one I'm going to choose for now. So we can now apply the result to the original unlabeled data set, or the full one that we had before. And we have that what we wanted. So this is already corrected zero-center data for X, Y, and Z axis, all in one picture. And the other one is the 000111 data in time. That is now another time sequence that we have. Let's take a closer look on this because we might not trust it. Well, where in most, at one point of the time, we were sure the data was off, the heat pump were off. We have the off label. We also have the off label most of the time where probably the thermal equilibrium was reached at least for a while. So the manual inspection of the results is quite satisfactory in my opinion. We can do more. With this new data, we can estimate the total running time just with a simple composite trapezoidal integration, which comes for a computational cost of a dot product, which is pretty fast. So all this interval has a total of about 480 hours, of which 275 hours was on a state on. And we can repeat it for any given interval. So for each hour, for each day, we can have a percentage on how much did the heat pump actually work. And so directly proportional, as I told you before, to the electricity consumption. So, in conclusion, I would fix some take-home messages to always sit down and hear the stories from your data because it can be fruitful. Label data, alas, does not exist in nature. You have to do the labeling for yourself or having someone having done for you before. So, and sometimes you have to be a little bit creative to label your data, or maybe some very well chosen subset of it. You have to be careful about that subset thing. I like this music actually. It's every half an hour, so I can know what time is it. Okay. Here the story of the data could be boring at the first glance, but if you start doing it, it will be very fruitful for you because you will know what your data is. And I like very much when working with other people that knows the data better, talk to them and let me hear what is the environment, how does the environment looks like, what are his opinion on this data, even if totally untrained on data science. It's a bunch of very fruitful and nice information to have. So the surrounding information are good to collect. As a future work, I would like very much to give non-binary label to the heat pump activity. So the heat pump could be on, but not so much on at this very max level, and I want to estimate that. I would like to compare the estimate working hours with some real measure of the electricity consumption to give a real sense of what's going on in these terms. And I would like to stop with the gifts. No, not going to happen. Now, I want to thank my colleagues at Fire Networks for the continuous support they have given to me in this and other works of mine, and for having developed some of the software that saved me a lot of works. Lara is one of them. I also want to thank the Sant'Agostino Clinic Network, from which the dataset was recorded, and in particular Andrea Codini for his availability and for having told me the story of the data actually. And finally, thanks to the organizer and to the audience, of course. Thank you very much for listening to me.
Thank you very much, and we do have time for questions. First one comes already.
Thank you for the presentation. So you said that you are using a train test split for computing the performance of your model. So this brings me to two questions. One is, have you tried using cross-validation to have like error bars on this evaluation? And the second one is, do you think it's important to have a causality in your model, in the sense that if you are making your train test split, you don't want the samples to be taken at random inside your time series, but do you think it's important to have causal effects, like don't interpolate between time series, but use something with windows that preserve what came before and what came afterwards?
Thank you very much for your question. The very first answer is simply to answer, no, I did not, but it's kind of a very good idea and a good suggestion, so thank you very much. The second one comes maybe with some misunderstanding about the data. In this moment, I am not counting which data come first, each one, and after. So I'm not taking into account, by choice, the sequentiality of the time series of the data. And I decided not to do it because it was, in my opinion, a matter of oscillations and state, or single state, instead of taking into account a sliding window. But the sliding windows is indeed a good idea to do, especially with time series in general. So that could be, again, one good suggestion for refining this work and make it work better. Yeah. Thank you very much.
Any other question? No question, everybody's hungry? Okay, then thank you very much again. And we go to the break, and again, please just take the supply of food and drinks from downstairs. Upstairs is for a different event.